Now see here magnetic dipole moment of revolving electron. So see here, this is the nucleus having the the positive charges Ze, and electrons are revolving around the nucleus. So see here, when the electrons move, they constitute current. So these revolving electron are actually producing current. So the electrons are revolving in anti-clockwise direction. So the current is here I in this clockwise direction. Now the magnetic dipole moment due to this current is that is into the plane of the paper, that we can write cross here, and that is given mu L. So magnetic dipole moment due to this current is mu L. This is the basically symbol used for this, and this is the cross is the direction is into the plane of the this board that is away from you. So now we have to calculate magnetic dipole moment of this revolving electron. So we know here I is equal to E upon T, we can write, that is basically Q upon T. Q we can write E, so I is equal to E upon T. Radius we know it, so we can write I is equal to E upon 2 pi r, and this is V. V is the orbital speed. So we have written this. Now the magnetic dipole moment mu L can be written here I into A, current into area, that is here we can write E V upon 2 pi r into pi r square. So this pi will get cancelled. You will be getting mu L is equal to E V r upon 2. Now if we multiply the mass of the electron and divide by mass of the electron, so we will be getting here E m V r divided by 2 m, where m is the mass of electron. So we can write here mu L is equal to minus E upon 2 m, and it can be written here mvr can be written the angular momentum, which can be written here L. So negative sign is here used because the angular momentum and magnetic dipole moment are acting opposite to each other. So we have calculated magnetic dipole moment of this revolving electron. L is here angular momentum. So in scalar form we can write magnitude E upon 2 m into L. L is angular momentum. According to Bohr's theory, we can write L is equal to nh upon 2 pi. So angular momentum of the electrons or the orbit is actually the integral multiple of the h upon 2 pi, where h is known as here Planck's constant. So by putting the value of L, we can get mu L is equal to E upon 2 pi, that is nh upon 2 pi, and here that is 2 m, not here this is 2 pi, 2 m. So we can write here mu L is equal to NEH upon 4 pi m. Now see here, this everything is constant here. If you put the value of the electron, charge of the electron and Planck's constant, pi and mass of the electron, these are known, or everything is given. By putting all these values and n is equal to 1, you can get mu L is equal to, that is EH upon 4 pi m. By putting all the values we can solve and get 9.27 into 10 raised to power minus 24 ampere meter square. So this is the minimum angular momentum of the orbiting electron. So we can call it, this is the minimum orbital angular momentum. So this quantity here, this is minimum orbital angular momentum, that means EH upon 4 pi m is known as here Bohr magneton. So this is about here the Bohr magneton. So the minimum orbital angular momentum is known as here Bohr magneton.